Hi, Algebra 2. We are going to talk about logarithmic and exponential functions. You guys started graphing these the other day, and what you're hopefully starting to notice is that they sort of look opposite each other. And we sort of hinted at the fact that opposite meaning they look like they are an inverse of each other. Remember, they look like a reflection over the y equals x line. So we're going to talk a little bit more about their properties today. What I would like you to notice for your notes is anything in a red box today. So there are 4 items in a red box, and I want to make sure you guys really understand the 4 red box items. Those are the most important, so I want to make sure that I show them in a red box. A natural logarithm is your first definition tonight, and a natural logarithm means it's the inverse of an exponential function. So a natural logarithm is designated by an L and an N. Natural log, I know it's backwards, ln. But ln of x, if you graph that, so if I do y equals ln of x, this is a natural log. And if I took the inverse of a natural log, I wind up getting y equals e to the x, which is what we were graphing the other day. We graphed both of these actually. So natural log, this is exponential, and they are inverses of each other. Okay, so that's why when you guys graph them, they wind up looking like they are reflections. They are inverses of each other. So a natural logarithm is the inverse of an exponential graph. If you're using your calculator, you can go ahead and just press the ln button. With your calculator, the natural log button is right here. So you can literally just push ln, make sure whatever you want to put inside of ln, is in parentheses, and then we just close the parentheses. So natural log of 5 is 1.6094. So we want to write down 4 decimal places. Go ahead and pause here and see if you guys can find the rest. So what we're looking for is natural log of 5, natural log of 0.5, and natural log of 3. Again, this is just what does the natural log function do? What would those values be along the curve that we were just looking at, right? Along that curve. What would the y values wind up being? So these are the 3 y values that you should get. These points are also along the curve. So if we take a look at our graph, if I graph the natural log of x, so not picking a certain number, just putting in x, and I graph it, I get this picture. Remember when you push trace, if I want to find the natural log of 5, enter, there's my y value, and that's where it shows up along the curve. If I want to find 0.5 as my x, there's that y value, the same y value that we found with the calculator without looking at the picture. And then the last one was 3. Natural log of 3. There it is. So it's just tracing the curve as you put in different x values. Now that we know how to use the natural log button and the function on our calculator, let's take a look at our second red box tonight. We are taking a look at 2 special rules with natural logs and exponentials. Because they are inverses of each other, they have 2 special rules that work with them. Since they are inverses, anytime that e is a base, remember e is a base, so it always has to have an exponent. If e and ln are next to each other, e is the base and ln is part of the exponent, right next to each other, they will cancel each other out because they are inverses of each other. So we will be left with just a, which is the leftover part, right? The e and the ln will cancel, and a is our leftover. The same with natural log. Natural log needs to have an argument, which means something will have to be put inside as the domain of the natural log. Every time you push ln on your calculator, parentheses pop open. So if we put e inside of the natural log, again, natural log and e will be next to each other. When they're next to each other, they cancel out. So again, we're just left with the part that's not the ln and the e. So we can use these 2 rules to try to solve for x. If we're asked to solve the following equations, let's do one at a time. I am trying to solve for x, but x is in the exponent. If I want to get that x, I'm going to have to get rid of this e. Well, I know that if I put e inside of the natural log, I can get to that exponent, which is the a in this case, x for me. So what I'm going to do is I'm going to go ahead and take the natural log of the left-hand side. But anything I do to one side, I must also do to the other side. So I now have ln and e next to each other, just like in this rule. So now I'm only left with the exponent. And x is equal to the natural log of 6. This is appropriate to leave as an answer, but I can also put the ln of 6 in my calculator and get a decimal. For number 2, my x is right here, and it is inside of the natural log. Well, since I already have a natural log, how can I get rid of a natural log? If I raise it with an e. So if I make e the base and the ln of x becomes the exponent, then these will cancel out just like in this example up here. So whatever I do to one side, I must do to the other side. So those cancel out, and all I have is x is equal to e raised to the 4th power. Again, e to the 4th power is an acceptable answer, but if you would like to find a decimal approximation, I can also put that in my calculator. Number 3, I have an e, and my e is raised to the ln. If I look right here, I already have my rule, my first rule, which means e to the ln will cancel, and I will get 2 is equal to x. So I've already solved. So in all of these examples, it's got part of one of the rules, right? If I have an e, I need the ln. If I have an ln, I need the e. And on this one, number 4, I already have the ln and the e, so all I'm left with is that 3 is equal to x. All right? So this is how natural logs and e's wind up working together. Because they're inverses, they have special properties that allow them to show their inverse properties, right? All right, now we're going to start with something you guys know, the review. This is from our last couple units. If you guys have x raised to the 3rd power, how do I isolate x? And what we were talking about is that if you have x to the 3rd power, I would need to take the cube root in order to isolate x. Whatever you do to one side, we must do to the other. Remember to put the 3 there as the index. So I will get x is equal to, what number times itself 3 times makes 8? So I get 2. Great. Well, in this problem, x was the base, right? And 3 was the exponent, and then we had 8 as our answer. What would happen if the 3 became the base and the x became the exponent? And it equals 81. This is called an exponential equation. Anytime that you have an x as your exponent, this is called an exponential equation. And we've already started to graph some of these, so we sort of know what they look like, right? They increase very, very fast. So what we're trying to do is, well, if I have a base of 3 instead of x, and I have an exponent of x, so if these switch places, how in the world am I supposed to solve for x? Because x is now stuck in the exponent. Well, since we know this is called an exponential equation, we know the inverse of exponentials is logs. Our last box for today, is that if you guys have an exponential notation, which is what we were just looking at, you can actually rewrite it using a log. Now, this isn't a natural log because natural logs only deal with e. However, base e. However, this one is a base of 3. So all we have to do is look at the pattern. If I have a base of 3 raised to the x power, what's going to happen is my base of 3 is going to become the base of my log. X moves as my answer, okay? And 81, which is what I was set equal to, becomes what's known as the argument that goes inside of the log. This is where your parentheses would be if you were using your calculator, okay? So the 3 is the base, and it still is the base. It's the small little number. The exponent goes to the other side of the equal sign, and the 81 is now our argument inside of. So here's our base, and this is our argument. And then over here is our solution or our answer, however you'd like to say. All right? So really, every single time that we're changing from exponential notation to logarithmic notation, we just have to follow that pattern, whether we're going backwards or forwards. How would you guys read the logarithmic notation? This is called log base of 3, base 3 of 81 equals x. So if you guys were going to read that out loud, that's how you would say it. And then what is the logarithmic equation? What does it really mean? Well, what it's asking you is 3 raised to what power would give you 81? So you guys might actually already know the answer to that, right? 3 to what power makes 81? Well, 3 times 3 is 9, times 3 is 27, times another 3 is 81. So in this case, x equals 4. However, they're not always going to be so simple to solve. So we might need to rewrite it as a logarithmic equation so that we can actually find it using our calculator if it's something that we can't necessarily solve by hand. So we're going to end with just practicing moving. So we're going to convert from exponential to logarithmic form. So here's my form. I'm going to use log, and remember this base becomes my base for the log. The exponent goes to the other side, so this x goes to the other side of the equal sign, and 64 is my argument. For number 2, again, log, base is going to be 1/2, little small sub number is 1/2. The -5 goes to the other side, and then 32 is my argument. Log base of 7, and the a plus 2 goes to the other side, and 343 is my argument. All right, now let's go the opposite way. If I'm going to convert from log form to exponential form, all right, I'm going to start with my base because my base is easy to find here, right? Base is 7. Now, this was my base. My exponent was on the other side of the equal sign, so that means it's going to be raised to the second power, and it equals 49. Okay, so 7 raised to this power equals that number. Kind of goes in a little circle. 2 raised to the x power equals 64. And then 9 raised to the second power is equal to m. So when we see you guys next time in class, we are going to try to convert these, and then we're also going to solve for x if x happens to be in the problem. All right? Have a good night.